Okay, for Chapter 13, Section 4, we're going to do motion in space. So we can use these vectors and their derivatives to calculate things in space. So the first one is r of t equals t5 plus 1, t9, and t5 minus 7. And it wants the velocity. Well, the velocity is just the first derivative of the position vector. So this is going to be 5t4, 9t8, 5t4. Any constants go to 0. So that's the answer for the velocity. Acceleration is the first derivative of velocity, or it's the second derivative of position. So it's going to be 20t3, 72t8, bringing these powers down and then subtracting 1, and then 20t3. That's your acceleration. Now the magnitude of the velocity is going to be the square root of each of these terms squared. So it's 5t4 squared plus 9t8 squared plus 5t4 squared. That's going to equal 25t to the 8th plus 81t to the 16, double that power, plus 25t to the 8th. Now there's a common t to the 8 in all three terms, so you're going to factor out t to the 8th. 25 and 25 adds up to 50. 81 t to the 8th, square rooted. T to the 8th can come out of the square root as t to the 4th. And we're going to have 50 plus 81 t to the 8th still stuck in the square root. And that's as simplified as you can go, so there it is. Okay, so that would be the magnitude of the velocity vector, which we call the speed. So that's called the speed. Okay, same kind of deal. So we're told position vector is only 2 dimensions, that's nice, minus 1/2 t squared, comma t. Therefore, the velocity vector is the derivative of this. Bring the 2 down, cancels with the half, so it's minus t. Derivative of t is 1. Acceleration vector is the derivative of this, minus 1. Derivative of 1 is 0. So that gets us this answer, and then again they want the speed. So the magnitude of the velocity vector is going to equal the square root of minus t squared plus 1 squared, which is the square root of t squared plus 1. Nothing simplifies. So there it is. And if you plot this, the position vector is a sideways, because it's minus 1/2 t squared in the x and t in the y. It's a sideways parabola, points left. And then the easiest way to find it is using the velocity vector. So the velocity vector would be negative t1. So if t is, t is 2 in this case, so the velocity vector should be negative 2 comma 1. Well, that's going to point 2 to the left and 1 down, so it should point like this. Oh, not 1 down, 1 up. So that's why I'm looking at this. That's not right. Okay, so this should point 2 to the left and 1 up, so it should go up and to the left like that. That's your velocity when t is 2, and the best picture is right here. Notice that your acceleration is always just 1 left, 0 up or down. So your acceleration is always left 1, 0 up or down. So it's an arrow that just points right to the left. So that's right here. So your best answer is this picture here. Okay, problem 3. Find the velocity and position vectors of a particle that has the given acceleration and the given initial velocity and position. So this is going to go backwards. So we're going to have to use the antiderivative. So the velocity is going to be the antiderivative of the acceleration with respect to time. Okay, and they tell us the acceleration is 2, 6, 6t, 12t squared. So we're going to have, this is equal to the antiderivative of 2 in the I plus the antiderivative of 6t dt in the j plus the antiderivative of 12t squared dt in the k. The antiderivative of 2 is 2t in the I. But we have to add a constant because we don't know, we don't have limits on this. So without limits of integration, we have to add some constant c1 in the I direction. Plus, the antiderivative of 6t would be 6t squared over 2, or 3t squared, plus c2 in the j. Plus, the antiderivative of 12t squared would be 12t3 over 3, which would be 4t cubed, plus c3 in the k. But then they tell us, if your time is 0, the velocity collapses to just the I vector. So if all my t's become 0, and the only thing that's left is I, that means C2 has to be 0, C3 has to be 0, and C1 has to be 1. Okay, because when we plug in 0 here, this 2t goes away, 3t squared goes away, 4t cubed goes away. The only thing I should have left is 1I, therefore C1 has to be 1. So the velocity vector is 2t plus 1, right there. 3t squared with nothing, because C2 goes to 0, and 4t cubed plus nothing, because that one goes to 0. So that's your velocity. Now, your position is the antiderivative of that. So it's going to be the antiderivative of 2t plus 1 dt in the I plus the antiderivative of 3t squared dt in the j plus the antiderivative of 4t cubed dt in the k. Well, the antiderivative of 2t is t squared. Antiderivative of 1 is t plus another c1 in the I. Antiderivative of 3t squared is t cubed plus c2 in the j. Antiderivative of 4t cubed is t4 plus some c3 in the k. And they tell us that the initial position when time is 0, you get 6j and negative 5k, which means C1 has to be 0, because all these I terms are going to go away when t is 0, because there's no I term here. And t cubed will go to 0 because we're letting t be 0, but there should be 6j, therefore this has to be 6. And then by that same logic, this t4 goes away, and I want minus 5 in front of k, so this is minus 5. So the position vector is t squared plus t, right here, t cubed plus 6, t cubed plus 6, right there, and t4 minus 5, t4 minus 5 right there. So these match what I've written right there. So that's going in reverse using antiderivatives. Oh, problem 4 is a nice one. It's not hard at all. What force is required so that a particle of mass m has a position function r of t equals t cubed plus 2t squared plus t cubed? So force vector as a function of time is mass, which is a scalar, just a number, times the acceleration as a function of time. And if we know r is t cubed 2t squared and t cubed, then v is 3t squared, 4t, 3t squared, which means A is 6t, 4, and 6t. And then the last thing is just to put an m next to each of these, so we call it 6mt, 4m, 6mt, which we have right here. And I wrote it in I, J, and K. So you can write this vector format into I, J, and K with, so it's 6mti, 4mj, and 6mtk. That'd be problem 4. Okay, for problem 5, it's really just kind of a follow along, and we'll use 5 to help us do 6 and 7, but they're going to kind of walk us through this. So they're going to say a projectile is fired with muzzle speed 250 meters per second and an angle of elevation of 45 degrees. So the idea here is, usually they draw it like a cannon. So we have this cannon here, and we fire out a projectile, and that thing is going to go like that. And it comes out with an initial velocity of 250 meters per second. And its angle, this angle here, is called the angle of elevation, and it happens to be 45 degrees. Well, we can break that into sine and cosine. So we can break this into what component goes straight across and what component goes straight up. And it turns out that cosine and sine will figure out those two directions. So the x direction is just this 250, which is really like a hypotenuse, times the cosine of the angle. So if they're saying 45, that's really pi over 4. And 45 cosine of 45 degrees is square root of 2 over 2. So this is really like x equals 250 times square root of 2 over 2. This 2 will have 250, so it's 125 square root of 2. And then with a t in front of it. So the original equation had the initial velocity, cosine of the angle, and t. Okay, and then we'll do the same thing with sine. However, and I missed this, they said that this firing position, so this starts, this position here is 10 meters above the ground. So the projectile actually starts all the way up. And so the equation becomes the initial height, 10 meters, plus this exact same breakdown, initial velocity times the sine of the angle times t, so very similar to the x component, minus the gravity term. So gravity is going to act against this thing, and the gravity term is 1/2 times squared times the constant for acceleration of gravity, which in metric is 9.8. So if you just figure that sine of pi over 4 is also root 2 over 2, you're going to get the same thing, 10, 125 root 2 t, so 10, 125 root 2 t, it's the exact same as the x term, minus 1/2 of 9.8 is 4.9 t squared. Okay. Then they're going to say this thing is going to impact, so it impacts right here. Well, at that point, the y value is 0 because it's back down to Earth. So what we do is we say set this equation right here equal to 0. Now this is a quadratic equation where a is negative 4.9, so let me write that. A is negative 4.9, b is 125 root 2, and c is 10. And you're going to run all that through quadratic formula. And they did that for us. So they set it up. So here's the quadratic formula. And all you have to do is do this on your calculator, multiply these numbers, add these things up, and you should get the answer right there. So this says that's the t value. After 36 seconds, this cannonball or whatever this is, this projectile will come back and hit Earth. Okay, and then they just want you to figure out, well, what's the x distance? So take that time and plug it back into the x equation right there. So you'll take 125 times root 2 times this 36.13 and you'll get 6,300 meters. Okay, and then we can write the velocity of the projectile. So we know x and y as functions of t. So we just have to take their derivatives. Actually, do they want us to do, is it that complicated? Okay, yeah, they do. So the derivative of 125 root 2t, the t would go away, so it's 125 root 2. The derivative of this would be 10 goes away, 125 root 2 would stick around, the t goes away, that's this component here, and then minus 4.9 times t squared would become double the 4998 times t, right there, with the minus sign. So that's the derivative. Then the last thing is they want us to find the magnitude of this derivative when the time is 36 seconds. So you plug 36.13 in for t right here. And then you get two numbers, you square them, add them together, take a square root, and you get 250. So this is interesting. It's launched with 250 meters per second, it lands with 250 meters per second. That assumes no wind resistance. So if you were to like fire a projectile in space and there's no wind resistance, the firing velocity would be exactly the same velocity if it hit something. So there's nothing to slow it down basically. Gravity doesn't slow it down, it just redirects it. So it fires up and then gravity redirects it back to Earth, but it doesn't slow it down, it doesn't speed it up either in this case. It's going to hit with the same velocity that it left because there's no wind resistance. Okay, so that's problem 5. Okay, so problem 6 is basically the same thing, but we have different numbers. So x, what we learned in the last problem, is the initial velocity times the cosine of the angle of elevation times t. Y is the initial velocity times the sine of the angle of elevation times t. And is that all we need? Yeah, that's all we need. Okay, so, and again, this picture, if the thing's not raised up at all, we're going to fire, and it's going to go up and come back down. And so this initial velocity is V0, and this is the angle of elevation theta. Okay, so this tells us V0 is 190 and the angle of elevation is 60. So, oh, I forgot a term here. This is minus 1/2 the acceleration of gravity times t squared. So gravity's pulling it down. So when we plug in what we know, this is 190. Cosine of 60 degrees, which is pi over 3. So where does it say 60 right here? Pi over 3 times t. And y is going to be 190 sine pi over 3 times t minus g is again 9.8, so this is going to be minus 4.9 t squared. Extremely similar to the last problem. The only difference is the angle's slightly different, and the y has no elevation, so that 10 in the last problem is 0 now. So there's no initial height. Okay, it says find the range of the projectile. So the range is going to be oh, let's actually simplify this even more. Cosine of pi over 3 is 1/2. So this is 190 times 1/2 times t, which is 95t. Pretty simple equation. For the y term, sine of pi over 3 is root 3 over 2. So we get 190 times root 3 over 2 times t minus this 4.9 t squared, which equals 95 square root of 3t minus 4.9 t squared. Okay, now to figure this out, to figure out the range, we have to figure out this time when the y value is 0. So the y value is 0 at time 0 in this case, and then again when it hits at the end of its trajectory. So we're going to set the y value equal to 0 and get 95 root 3t minus 4.9 t squared. And to do this, we're going to factor out t. And this is 0 at 2 points when t is 0, which we already knew. So if this t is 0, the whole thing goes away and becomes 0. Or when 95 root 3 minus 4.9 t equals 0. So if this bubble is 0, then the whole thing is 0 also, which gives us 95 root 3 divided by 4.9 equals the t value. And if you do this in decimal form, I got this time is 33.58 seconds. And to find the x distance, we're just going to plug this time into this equation right here. So the x distance is 95 times 33.58, and we're going to get the distance is approximately 3190, what are we doing? Meters. Okay, right here. Okay, the maximum height, there's an easy way to do this and a hard way to do this. So I'm going to do the easy way. The maximum height should occur exactly, it's right here, exactly halfway in between these two times. So if this time is 33.58, this time is 33.58 divided by 2. Now this only works because we're firing from the ground. If we're firing from a height, this is not true. Okay. And if you divide 33.58 divided by 2, you should get this time where it's going to hit the max height occurs at this will occur at 16.79 seconds. So to find the height, we're going to plug that into the y equation. Let me start fresh because we're running out of room. So let me rewrite y. The y equation was 95 root 3t minus 4.9 t squared. And we know that it hits its maximum height when the time is 16.79 seconds. You square that, multiply by 4.9, subtract that from this, you should get the maximum height is 1381 meters. Okay, now it wants the speed at impact. The speed at impact is magnitude of the velocity vector. So it's the square root of 95t squared plus 95 root 3t minus 4.9 t squared squared. And the time is that 33.58 seconds. So you just have to plug in 33.58 into this t and this t and this t and square it and add all these numbers up, square, add, square root, and you should get 190. And guess what? That was what it started with. So we fired at 190, it lands at 190, so you probably could have got that without any arithmetic at all. But you can prove it's true. Okay, 7 is much more involved than I hoped it was going to be. So I will say there are no red numbers here, which means this problem never changes. You can look at it, it's a bear. This is the answer, you can plug that in and get it right. If you're really interested in seeing it, you can ask me and I'll show it to you, but it is, it's a ton of work, and it's a little more than I would want us to worry about. So let's skip that one for now. You can use those numbers, they should give you the right answer. Let's go to 8. Okay, so it says the position function of a spaceship is 5 plus t, 3 plus ln t, 9 minus 4 over t squared plus 1. And the coordinates of the space station are 8, 5, 11. The captain wants the spaceship to coast into the station. When should the engines be turned off? So this one, okay, so how would we do this one? We would say that we want this position vector plus some scalar times the velocity vector has to equal, we can make this a vector by just writing it as 8, 5, 11, because if we assume that the spaceship is at the origin, then the vector from the spaceship to the space station is just 8 minus 0, 5 minus 0, 11 minus 0. So it's like a vector 8, 5, 11. Okay, so we need the velocity vector of this. It is going to be, and let me write it in vector form so I don't have all these ij's running around. It's going to be 1. The natural log of t is 1 over t. Derivative of natural log of t is 1 over t. Then, this one's a doozy. It's going to be 4 over t squared plus 1 is going, and it's negative, is going to be positive 4. I'm going to write it, and you might have to do this yourself to prove that it's right, but let me just write it for the sake of time. You should get this, 4 over t squared plus 1 squared. So that's a calculus 1 problem, the derivative of that, and I'll let you confirm that that's correct. Okay, so let me see, where am I now? Okay, and then we're multiplying this velocity vector times this s, some scalar, to stretch this velocity so that when I add it to the position, it gets me to the space station. So s times v of t will be s over t and 4s over t squared plus 1 squared. It's supposed to be an s right there. Okay, so s's show up. Now we're adding that to the original position vector. So now we're saying add r to each of these. So I'm kind of building this solution as I go. So this is going to be r, which was 5 plus t, so it's going to be 5 plus t plus s. The second component of this was 3 plus natural log t. So it's 3 plus natural log t plus s over t. And then the third component was 9 minus 4 over t squared plus 1. So it's 9 minus 4 over t squared plus 1 plus 4s over t squared plus 1 squared. Oh, I forgot a 1 in there, I think. Okay. Okay, so that is this. And we're setting this equal to 8, 5, and 11. So this whole thing has to be equal to 8. This whole thing has to be equal to 11. oops, 5, the middle term, 5. And this whole thing has to be equal to 11. Now the first one gives us a pretty simple equation. So it says 5 plus t plus s has to equal 8. So let me write that. 5 plus t plus s has to equal 8, which means t plus s has to equal 3. And we're going to solve for s. So s equals 3 minus t. So that gave us kind of a solution for one of the letters. And now, because natural log is difficult to work with, we're actually going to solve the third equation. And we know what s is. So we're going to have 9 minus 4 over t squared plus 1 plus 4 times s. But we know s, it's 3 minus t over t squared plus 1 squared has to equal 11. And probably the easiest way to solve this, I suppose, is to multiply everything by t squared plus 1 squared. So you get 9 t squared plus 1 squared plus 4 t squared plus 1 plus 4 3 minus t equals 11. So if you look at that, multiply every term, oops, I forgot a term, 11, t squared plus 1 squared. So if you multiply everything by t squared plus 1 squared, any number without that gets the entire term. Any number with part of it gets part of it, and then this third term had the t squared plus 1 squared on the bottom already, so it doesn't get anything added to the top, so you get this. So we have to FOIL, combine like terms. I'm going to kind of skip that. I'm going to assume you can do FOILing and combining like terms. You will get 0 on one side, t to the 4th, 8t squared. You can confirm this, try it out with my numbers. 12t plus 3. And when you solve this, you will get t is equal to 0.31847, and you'll get t equal to 1. And if you check these, it turns out that only one will work. In fact, we can check it pretty easily in the second equation. So we use this first equation to get s. We use the third equation to solve for t. And let's use the second equation to check it. So the second equation says 3 plus natural log of t plus s over t. So that's going to be 3 plus natural log of 1 plus s over 1, but s was 3 minus t. So this equals 3. Natural log of 1, you can confirm in your calculator, is 0. So 3 plus 0 plus s over 1 is just s, but s is 3 minus t, and t is 1. So we get 3 plus 2, which is 5, which is the same as what we wanted it to be. Okay, so that proves that t equals 1 has to be the solution, and there you go. And we'll get to the space station. Okay, last two are multiple choice, or true false. If the magnitude of the radius vector is 1 for all t, then the derivative of the magnitude of the vector is a constant. So that does not have to be true. So just because the magnitude of your vector turns out to be 1, that doesn't mean that the derivative of that vector magnitude should be some constant. Okay, last problem, determine whether the same is true or false. If the magnitude of the position factor is 1 for all t, then the derivative of that is orthogonal to r of t for all t. Now that one is true. And so if you have the magnitude of some position vector is 1, the simplest drawing I can make is a circle of radius 1. And any derivative you draw here will be orthogonal to this radius 1 circle. So that's probably the easiest way to show that one's true. Okay, that will complete section 13.4.